Okay, so I have your exams, and they'll come back maybe Wednesday-ish. And I also have a take-home quiz that's due next Monday here that'll reinforce some of the problems from the exam. But today was kind of an in-between lecture because it talked about epoxides, which we've talked about a lot, right? That was the lecture, and that was the online quiz. So what I'm going to do is we're going to put our knowledge of epoxides and other things to work. So drug design, right? A lot of organic chemists work in drug design. More of them work probably with polymers or plastics, and we'll come back to that later on. But certainly pharmaceutical design, drug design is a huge area for organic chemistry, and it might be something that you're interested in down the road, either in prescribing or taking or making. So a lot of work goes into drugs. So I got in the mail something about one of the drugs that I take for I'm going to HIPAA violate myself here. One of my diabetes drugs that keeps sugar from being absorbed, and it basically passes out of the body in the urine. And it's called Invokana, if you've ever seen it on TV. And they sent me this packet of information because they were renewing my whatever for it. And they said, read through this and ask your doctor if you have any questions. It was a very thick envelope because there were 3 papers this big, and they were not the same. They're not one in English, one in Spanish. They're all in English. And they are 2-sided. And none of the 3 pages are the same. Now, I don't know if you didn't have a PhD in organic chemistry, how you would even begin to look at that. But, there's some good information in here. We've got, since this one is a 2-part drug, there's this part right here called whatever that is, and that is an inhibitor of the sodium glucose cotransporter, SGLT2. I know enough biochemistry to know that's how they abbreviate everything. And then it's got its chemical name. There's a 1S in there. So there's actually a bunch of chiral centers here. And then that goes with this, which is called metformin, which is a very cheap and very small drug for diabetes. And then it goes on to all sorts of stuff like the pharmacodynamics. There's all sorts of data in here about drug interactions with a bunch of these. You don't need, if you take acetaminophen down here, I can take up to 1,000 milligrams of acetaminophen, which will probably do other bad things for me. But there's no. So this is part 1 of 3 that I am supposed to read through. And if I have any questions, take it to my doctor, which actually I will do, because she kind of has a weird sense of humor. She first asked me, like, what do you do? And I said, I teach chemistry. And then she's like, like general chemistry? And I go, no, organic. I usually don't release that information that readily because every doctor says, I hated organic chemistry. Which she said after she said, well, that must suck for you. And I said, it doesn't suck for me, maybe the students, but I'm perfectly fine with it. And then she told me how she hated it, how she only went to class because her professor looked like Gabriel Byrne. I think I know who Gabriel Byrne is. He's not David Byrne from the Talking Heads, which is an 80s reference. But so she's got a little different sense of humor and a little different sense of bedside manner. So I'm going to take these to her, and I'm going to say, this said that I should talk to you about this. And we'll see what her response is. Because her response is going to be, well, you have a PhD in organic, you can just read through it. So, this is one drug. And it's still full price. It hasn't gone into generics yet. So whoever's making this, and I forget who it is, they're making full price. Okay. Now, the discussion about drugs and social justice and all of that, I could talk about that in class because I am covered by academic freedom, but you can talk about that in other classes. But there's a lot of work that goes into a successful drug, let alone one that's not successful, and how you get to that pathway. So that's just the example of that. So I'm going to talk about just for a couple minutes here, and then I'm going to ask you to figure some things out for me. When you're looking at the making of different types of drugs, in the old days, and this is probably 15, 20 years ago, I think it's done a little bit differently now, or hopefully it is. Drug companies would have hundreds of thousands of compounds on their shelves that they could use, and they knew what the structure were, and they knew they hadn't decomposed, and they had to figure out how to make them. If there's a chiral center in it, they probably needed both R and S, and they needed the racemic mixture. But what they would do is they would create sort of libraries of molecules. And it was pretty standard. You'd have a methyl, ethyl, propyl, isopropyl. You might have an OH or a BR or an ether in different positions in the molecule, and it would change the function of that or change the effectiveness of it. So here's an example that I found yesterday that's on PLOS One, which is an open line, or it's an open source journal. So what they were looking at was they were looking at a group synthesizing different, what they call derivatives or different analogs of the opioid fentanyl. Right now, opioids are all in the news, right? It's a big problem now, particularly in Ohio and really across the country. It's, I think, even bigger problem than meth was in terms of public health. So here are the structures of some opioids: morphine and tramadol, Demerol, and then fentanyl. I think the fentanyl stuff, that's what Michael Jackson, that's the last thing I think Michael Jackson took. I think that was his sedative of choice. So over here they have some of the fentanyl derivatives. So what you do is you look at what you think is the key part of the molecule, and then you start changing groups around that key part. Now maybe this is based on, they still teach you the lock and key method in biology, where you have a receptor, you've got a DNA or something, a protein, and you've got a certain shape that kind of fits in there and does something, sort of a receptor model. So they may know what the key thing is, and then they're trying to change the group to optimize its behavior, basically its chemical reactions. So what they did was they kind of changed over here, put an OH group, put an extra CH2 in an OH group, or put an OH group basically there. They put this, we'll talk about this one later. That's a that's sort of a pyrrole type molecule, thiopyrrole. They put a ester, and then they put the carboxylic acid, but they started adding groups into this carbon, like a methoxy. You've got a carboxylate, an ether, a methyl ether, and then whatever that is, that's a ketone. So they're kind of making analogs of these, and these analogs have been made, and it's kind of hard to see on the screen, but on your piece of paper, they looked at its comparison to, I think it's a comparison to fentanyl itself. So it looks like the top one's like 6,300 times more potent, and then 500, 100 to 200 times, and 1,000. So each one of these, when you make this analog, it becomes more potent than fentanyl itself. So you could take this kind of procedure or this kind of process and apply it to anything. Painkillers, cancer drugs, or curing whatever you want to cure. They use this approach to create these different analogs, and somebody has to synthesize them. Right? So back 15 years ago, there were tons of organic chemists in the lab making all these different derivatives. Maybe one person if they were really efficient, but most likely a team. Nowadays, I think they use combinatorial chemistry, and there's some other ways that they can do it. Not quite gene chips, but sort of an organic equivalent of gene chips, if you know anything about those. So this is the way kind of drug discovery was done back in the older days. Still somewhat done that way. So we change groups. So today we're going to play a little game. We are going to be a drug company. What's Dr. Setter's favorite? Is it the Marinovich company, or the Marinovich person? He does everything. I have various Marinovich derivatives. I've got the Organovich, the Perfumovich. But here's what we want to do in our drug company. We have this molecule right here that we think that if we change groups around these these 1, 2, 3, 4, 5 carbons, that we can get different activities of a drug. And so if I start thinking about, well, what could I do with those 4 carbons? I could think about, well, maybe I'll put a double bond in between each of those positions. I could put a bromine on each one of those positions. Now, I've left this one out. After Wednesday, you could probably put the bromine there. But right now, it's going to be a little bit of work to make that. I could put OH groups on each of those 4 of the 5 carbons. Then I could think about putting 2 bromines here, 2 bromines there, 2 bromines there, 2 bromines there, 2 OHs there. That's not it. I can now think about bromine and OH and switching their positions as I go across those 2 positions. And if I'm really overly ambitious, I can think about replacing the OH with something like an OCH3 or an OCH2CH3, an ether. So what I'd like to do is I'd like to make this whole library of compounds, starting with ethyl cyclohexane, so that I had it to do all my testing. So what I'm going to do is I'm going to give myself $60,000, $70,000 raise to group leader, a pharmaceutical company. I don't have long-term job security, but for today I'll take the increase in salary. And unfortunately, none of you guys have degrees, so you're not going to be paid as a BS chemist. Although if you're a BS biologist, a lot of biologists work as chemists out in the real world, so this is not out of the question. So you're my group. Sadly, we'll make it paid interns. And if this was a real group, some of you would be doing the testing, some of you might be using the computer to figure this out. Salaries add up really quickly, particularly if you all had degrees, right? That's part of the reason why they can afford to send me 15 pages of stuff about a drug, because it costs a little bit of money to do that. But again, discussion for another time. So what I want to know is, I want your ideas about how I can make this entire library starting with ethyl cyclohexane. That's what I want to know. Okay. So what I should probably do is, we should probably focus you a little bit more on Because if you're sitting there going, oh, all those? You expect me to make all those? Well, I expect somebody to make all those. That would be my guess. But let's focus it down a little bit more. So we'll start with a couple of things. In the first row, I've got double bonds, I've got OH groups, and I've got bromines. The first three rows. Actually, we can do the first three rows. But if you notice, I've got 4 compounds in each one of those first 3 rows. Right? I've got 4 double bonds, I've got 4 OHs and 4 bromines. So here's what I'm going to task you with to start with. I've got 1, 2, 3, 4 rows. My big dice are upstairs because the elevator is broken. But I do have a random number generator. So I got 4 double bonds. So how about this? Let's say that row number 1 here makes molecule number 2. So number 2 in all of those. So the number 2 alkene, let's look at it that way. The number 2 alkene. And then you can, if you want, you can make the number 2 OH or the 2 Br. This row right here is going to do the number 1 alkene. So again, you're starting with ethyl cyclohexene. Row 3 will make alkene number 3, and row 4, I guess, will make alkene number 4. So what I'd like you to do is to think about, and you can talk amongst your group. I mean, you're not going to talk about all eight people, but come up with some strategies, some reactions, some pathways to get to your alkene. Now, along the way, you may make the bromides or the OH groups that are down below. And if you use one of those, great. But if you don't, think about how you'd make your numbered OH or bromide. And then we'll go from there in terms of making the other molecules. So I will give you about 5 or 7 minutes to think about that. Feel free to discuss. And then I'll randomly maybe call on somebody in the row, or somebody in the row volunteer how to make each one. No, I think
Figure out how to add what if we oh wait. And then yeah. You have to add it. No, you have to add it. Yeah. Wait, is it just yeah. This is H2SO4 and then we take this is but I don't know if it's why was it one of them was like remember it's two like can't make it oh no more yeah.
So if it's not with so what if we are
Yeah.
No, it's not.
I mean, there's not as good. There's like a station part.
Well, that would be or, yeah, you can do that or worry about like page two or something.
As many steps as you want. You can use as many steps as you want since we're doing it on paper. Basically, we're brainstorming right now.
I mean, you could technically add one. And what about for this one?
You can't add HDR.
Yeah, you're gonna need H2O too because it has a lot.
There's only two reactions.
Oh, so
There's only two reactions you can do with alkanes. So if you try and do anything more than that, I'll just say no.
I don't know if that's
how does it go?
So here are two, as almost, as almost, there's bromine equivalents for everything that we've done before.
So we're just doing that one, that one. I don't know. Well, for the second, or for the fourth, the second and fourth one, with the VR, the 2 VRs, that is VRs.
It's gonna be without words.
Not scale, like
VR2.
Is it just VR?
Yeah, are you talking about for the first?
For the fourth one.
For VR2.
Yeah, because we'll don't do VRs add.
Right.
How do you add two?
Well, you can add it by order.
Well, because it's a
KMNO4, or sorry, not, yeah, KMNO4, OH minus, adds OH, OH.
Oh, okay, something like that, yeah.
OH2O, adds OH, OH. But how do you get to add cis in that position?
I mean, do we have to have an added cis? Isn't it specified?
No, but just how you can fill in an position.
Okay, so how are we doing with our brainstorming here? We think we're doing okay? You do? Well, then maybe we should see how maybe you can propose something to me.
First couple steps, I think.
Okay, so here's some other rules that I'm going to add to this to make this much more realistic. Number one, I want to basically only use reactions that will give me the product I desire as the major product. Because if I make more than one product, I'm going to have to separate it, right? Like we learned in lab, so maybe I have to do a column on it. I'm going to lose money because I'm not making the one compound. I'm making like 5. You could say, yeah, but if you separate them, well, I'm going to have to hire a couple more people to separate it. I'm going to have to test its purity. So ideally, I would like each reaction to give me the major product that I desire. Because in the end, I'm going to put each one of these in a bottle, put it on the shelf. I'm going to have to verify its purity. I'm going to have to make sure that it's what it is. So a lot of work is going to go into this. So, the floor is open. What would you like to do? I mean, each table was tasked at making each of the 4 alkenes. Table 3 said they were in good shape. I think we should test them. So how do you want to make alkene number 3? And you have your piece of paper. How do you want to make that?
Can we add BR2 at room temperature with light?
Okay, so I'm going to take the ethyl bromide, use Br2 and light. What kind of reaction is that?
Free radical.
I'm going to do free radical halogenation, and where's the bromine going to go?
It's going to go on the tertiary.
Okay, it's going to go on the tertiary position, so I'm going to make that. Is that the major product of that reaction?
Yes.
Yes, it is. Right? Remember, that's like 1,700 to 1. So, all the groups, all 4 of your groups, guess what? Your alkenes have to come from that. That's the major product. Okay, so we're going to want to make all 4 of those. We're going to want to make all 4 of those alkenes from that one. So how did you guys then decide to make alkene number 3?
Then we add tertiary butoxide.
Tertiary butoxide. Okay? We could add tertiary butoxide. And where's the double bond going to go?
We were hoping it would go on the one outside the ring, but with 3 substituents.
You want this?
Yeah.
Team, do we agree with that? Do we have more than just hope it'll go there? probably the best. That's probably the best of our ability, right? We got 3 substituents. We're hanging our hope on the fact that this group is going to be less sterically hindered than that group. We could say NH2 minus, right? Where's the NH2 minus going to go? It's probably going to go in both positions. Probably there and there. So I think we're going to have to bite the bullet and pay somebody to separate those two. If we can't make them more than 50-50, I think we're just going to have to separate the two of those. Unless you want to come up with another way of making each one of those an 100% yield. I don't necessarily see that right off the bat. Okay. So so either tertiary butoxide or NH2 minus. Oops. Either one of those will take care of the alkenes. What is that? 2 and 3? So did row 2, is that what you guys kind of, is that what you kind of proposed? Maybe to make number 2? Wait, what did you guys, oh, you guys had number 2. I should have gone 1, 2, 3, 4. Okay, so you guys were okay with that? Okay. Now, I guess the other two groups going to have their work cut out for them. So if we wanted to put the double bond here or there, any suggestions? If I'm saying that it has to come from that bromide, if it's got to come from the tertiary bromide, how am I going to get the double bonds into those two positions? Can I do it in one step? No, I can't do it in one step. Anybody have any suggestions as to how to get the double bond way over here? Well, how about this? Could I make this the double bond? I know how to make that double bond. I'm gonna spend a lot of money at purifying those two compounds, purify those two alkenes. Is there any way that I could take that alkene and maybe by a couple of steps turn it into number 4? Paul?
Do it where you add BH3 and H2O2, and I'll add the OH group to the
Okay.
the carbon at the end of the ethyl group, and then you add.
Well, hold on. Let's take a look at that. So BH3H2O2. What's that adding to the double bond? H and OH, right? So I'm adding an H and an OH. How? Anti-Markovnikov. So I put my H here and I put my OH there. Do we like that? Now that makes alcohol number whatever I wrote. So we just made an alcohol that we needed to make. And so now you want to turn that into the alkene by using what?
Then you can add like P and Cl3. PCl3 to replace the OH group with Cl.
All right, so let's add PCl3 or Actually, let's make that PBr3, since we're making bromines and chlorines, or bromines. And so we could turn that into a Br. So now we just made one of our bromides. And now what would you want to do with it? So now we're going to use our tertiary butoxide to make our alkene with the double bond at the end. Sound good?
Could you use tosyl chloride?
Could use a tosyl chloride if I wanted to. Turn this OH into a tosylate ester and then use tertiary butoxide. Sure. Now the disadvantage there is that I wanted to make this compound. Right? So I'm making one of my library compounds in this method. But in real life, we'd have to figure out which one's going to give us the highest yield, have the least waste, cost the least, make it as pure as possible. So yeah, that's another possibility. Okay, so now we just made alkene number 4. Great. So what do we got? We got alkene number 1. That is the second row, right? Have any suggestions on how we could make that one?
We have to use the first one, right? The major product.
Yes.
And, I don't have the answer.
What would be your idea if we didn't make this one?
Similar to the bitter step, but instead of using PBr3, use H2SO4.
So you want to kind of use this methodology right here?
I think so.
Okay. Could we do that from one of the alkenes that we just made? Better yet, could we do it from either alkene number, this is number 1, this is number 4, this one's number 2, and this number 3. We're going to have an abundance of 2 and 3. So could we make it from either 2 or 3?
I was thinking 2.
2, okay. So let's do that. So let's start with number 2. Now, what did group number 4 propose? Basically, they added something, and then they did a tertiary butoxide to put the double bond in the least substituted position. So
if you add the H2O2,
okay.
the OH group is going to move to the lesser substituted side. So it's going to move down.
So you're going to make that.
Yeah.
Okay, is that one of the alcohols we wanted to make? Yes. Okay, then what do you want to do?
Maybe. I was thinking H2SO4.
Okay, okay.
Move up.
H2SO4 is going to do what? Form a double bond, but it's going to
Yeah, it's going to back up.
go back up. So I want to make the double bond that's least sterically hindered, or least substituted here. What did they do?
They used PBr3 and then tertiary butoxide.
Okay, so let's use PBr3. And so now we just converted that OH into a Br. Did I want that Br? Yeah, that's one of the 4 bromides I wanted. And now we could use tertiary butoxide and make the least substitute double bond. Does that sound good? We all agree with that and that? Okay, so so we've made a number of compounds, right? We've made a number of OHs and bromides, and now we've made all 4 of our alkenes. So we've made number 1, number 4, we're going to have a ton of 2 and 3. We've made our bromide, how many of the bromides have we made? I think we've made 3 of the 4 bromides by using anti-Markovnikov H and OH addition and then converting the OH to a Br. And we've made how many of the alcohols? 1, 2, right? So how many more alcohols do we have to make? 2, right? I want the OH there, and I want the OH down there, right? I think those are the 2 alcohols we have left to make, right? Okay. Your choice. You can make either alcohol from, I guess, anything on the board. Although my choice, our ultimate choice is going to be one of the first 3 things that we made. Because we're going to send that to the factory, or we're going to send that to a plant. We're going to make a ton of that to use for all of the other steps. Can we make either one of those alcohols? Harris?
To make the first one, could you go back up to the alkene 3? Instead of adding the BH3, if you added H plus H2O.
So I could make that one from H plus and H2O. Do we like that? Markovnikov addition to that alcohol, or to this alkene? Seem okay? Everybody? Yes? Okay. Got one more left. Oh, wait. Oh, we don't have to make that one. I guess we'll erase it. Now, what's the problem? The problem is if I wanted to think about using alkene number 1 here, and I'm going to have a hard time doing Markovnikov and anti-Markovnikov because I'm going to get a 50-50 split. Right? Now, I could do the 50-50 split and then split them off into alcohols, those 2 alcohols I need anyway. But since we didn't have to make that, I guess we'll ignore it for the time being. Could we convert this guy, which is our number 1 compound that we're going to make a ton of, into that? So we could use hydroxide, or we could do water. I like that. Again, in real life, what would I want to do? I'd want to figure out, I'd probably have to bring in an engineer, and they make much more than chemists, to figure out how to optimize the process, which one's going to give us the highest yield, ultimately which one I'm going to be able to do most environmentally friendly. and most cost effectively, probably the cost before the environment, but maybe we want to run a green company, so we'll reverse that. We'll just charge more for our drug at the end. Or I'll pay you less. All right, so now we've made all of our alcohols and all of our bromides and all our double bonds, right? No? Which one am I missing? What other alcohol is there? Oh. This one? And with the bromide too? Well, if I can put the OH there, I can definitely put the bromide there, right? Should I even be messing with that? Yeah, I'm okay with that. I'm okay with making either one of those. How do you want to make it? Your choice. What do you want, Sarah?
You take the fourth alkene and add the H3, H2O2 so that it adds
Okay, so let's start with that double bond that we made. That was number 4, right? And I've got an extra group in there, which I've got to be careful of. So I take that double bond and I do anti-Markovnikov addition because I'm still using a molecule that's unsymmetrical, so anti-Markovnikov addition would work. So I could do anti-Markovnikov addition to add the BH3 and the H2O and put the OH group there. That works fine with me. So where's the bromide going to come from? PBr3, sure. We could use PBr3. Could I get from that alkene directly to that anti-Markovnikov bromide? Could I get from this alkene to this bromide in an independent step and not go through the OH? We've done a lot of we've proposed a lot of anti-Markovnikov additions of H and OH. Is there an anti-Markovnikov addition of H and Br? Yes? No? Can you add HBr anti-Markovnikov? Pretty sure you can. So what do we need?
HBr and H2O2.
HBr and H2O2. So there's another way we could get to the bromide. Okay, so now we made all our alkenes, we made all of our OHs, and we made all of our BRs. Okay, so now what's left? All the double OHs, all the double BRs, and then the combinations of BR and OH switched back and forth. Mitch?
I don't know if this could work, but like, make an epoxide out of it.
Could I make an epoxide out of it? Out of what?
I don't know. At some point there, you make an epoxide in there.
You're going to have to make an epoxide. We're going to need an epoxide at some point. We're going to need, why did I assign each of you, or each row, a double bond to make? Because we're going to need each one of those double bonds, right? So now we have to think about this. Can I turn each double bond here, like number 13 here? Can I turn that double bond into adding 2 BRs? Yes. Can I take the other double bond and make the next dibromide, the next one, and the next one? Yes. Can I add two OHs? How do I get two OHs next to each other from a double bond? Do I know that reaction? I do. But that's why I'm making significantly more money than you. In our mythical company. But I can do those in one step, right? So I'm going to need the epoxide if I want to have an OH and a BR. And I'm going to reverse the positions of the OH and the BRs. And so I'm going to need to convert the double bond to an epoxide to this. To make each one of those combinations. I should make this a take-home quiz. What do you mean, no? Since when is that up for a discussion? Well, considering I may or may not be able to write that up today, if we do that, I'll save it for the quiz for Friday. So we know there's 28 compounds here. We actually know enough reactions to make every single one of them. We collectively. Now what we've got to do is turn the collective knowledge into each and every one of our knowledges. But this is what people have to sit around and think about doing before they even go to the lab. Okay, I'll release the video, and there's an online quiz for Wednesday. There won't be an in-class quiz. But if you come up and you can come up and start your take-home quiz for next week.
This is due next Monday.
Yep, the date's on there.